So, good afternoon, everyone. My name is Siva Poornan. I am a doctoral student at the Civil Engineering Department of IIT Madras, and today we are meeting for the seventh time in this uh, course, Matrix Method of Structure Analysis. And this is a live interactive session where we discuss on the course content, any doubts that you might have, or on the assignments what has been given to us. So, uh, in the previous weeks we have been discussing, first we started with basic structure analysis. We discussed on the prerequisite for this course, the basic method of structure analysis, and then we went on to built on to displacement methods of structure analysis, where we discussed about stiffness methods and matrix methods. And then we gradually built the matrix method for trusses, then went on to beams, and then added frames to it. And we have discussed all these in the live interactive session as well. So particularly in the last week we had discussed on a particular specific problem that was asked in the previous week, on how to find out deformations that are happening between the nodes. Because one of the ways in which we develop matrix method is that we introduce nodes and then we give degrees of freedom to those nodes, and we are interested in finding out displacement at those nodes for forces given at those nodes. So basically the stiffness matrix relates the forces and displacements at the given nodes, and we do not much talk about what is the deformation that is happening within between these nodes. So in the previous week we discussed about how do we find out the deformations that's happening between these nodes using a concept called as interpolation or shape function. So in this session we will be probably discuss on multiple aspects on which is not directly related to matrix method of structure analysis, but to basic method of structure analysis as well. So before I get started, I would like to know if there are any questions on what we have discussed previously on shape functions, or anything else that you might have come across in the previous sessions.
No, no, no. It was quite
Oh,
clear.
okay, then we'll proceed on to this the discussion for this session. So before we get started, I thought we would just recap on analysis of truss beams and frames, which pretty much we have followed a similar procedure for all these structures. The basic method is that we first built the stiffness matrix for a given element, which can be a truss, a beam, or a frame, and then we first build it in the local axis, that is the axis of the member itself, and then we convert it into global axis using transformation matrices, which just says how much it's what is the angle of orientation. So it depends on that. Then once we have the global stiffness matrix for a particular element, we do the same process for different elements, and then we assemble them using compatibility conditions, because we know at what nodes they are matching each other. So we are able to assemble them, and then once we assemble them, we have the global stiffness matrix for the entire structure, which can relate the forces that are coming in the nodes for a structure to the displacements that are occurring at the same nodes for the same structure. So that's the basic idea of how we do this analysis. So now these all these procedures, now you would have seen that these are routine and we would be following a similar procedure, right? So these can be incorporated in a computer and we can automate it, so that once we define the structure, what is the material properties like Young's modulus, moment of inertia, length, area, as well as what is the inclination of these members and how they are connected. If these informations are provided, then we can, this assembling of finding out stiffness matrix and assembling them is all a routine process which can be automated, and the software or whatever program you write would be able to do that, and then it would give out the displacements of the nodes, right? So this all have, you can implement it in a, system program like MATLAB, Scilab, or it has been already implemented in different commercial softwares which you can take use of, and then you can apply it and get it. But then what is the purpose of learning all the basics if it has been already implemented in a software? So in the click of a button, we can get the answers. If we define a structure, it can analyze and say the displacements that are happening at different nodes. So then why do we need to learn it? Why do we need to learn how it does? Since somebody has already done it, somebody has already learned it, taken the hard work of programming it and writing a entire program for it, then what is the purpose of learning it?
I think basically we should be able to, relate with the results. For
Exactly, and
example, say there is a continuous beam and uh, the last span is being loaded. Okay, so the result should show that there is a clockwise rotation at the penultimate node. So if the software shows that it is a anti-clockwise moment, then is a mistake. There
yes.
should be some bug, or maybe we have not provided the input properly.
Okay. So you're saying something like if there is a moment here, then the rotation should also be something like this.
Yes, that
Depends on
from
other loads
our
as well.
basic understanding we should know.
Yes. So that is what I also feel, right? So basically, I'm sorry, I might have drawn it the other way. It's right. Yeah. So this is where we need to know structure analysis, right? So we need to know which direction it rotates.
Yes,
So the basic idea is that we need to have an engineering judgment of what whether the answer that the software gives is it right or not is
yes,
what we need to know, and there should be some basic checks that the intuition we should develop an educated intuition which comes only from knowing the basics of it, and that
yes,
is why it is very important to know how the machine does, because we are the master for the machines and we should know whether what it is doing is right or not, right? So
yes.
you might be able to say it better because you have worked in firms and you would be knowing that
So
software will
if
definitely
we
give
do
answers.
static check, with the old
Hmm.
the load cases, whatever we
Hmm.
have applied is being equal by the reactions or not. That is also one
Yes.
check.
Yes. So you should know immediately. You should able to get a free body and say that okay, the forces are all matching. They are in
Yeah.
equilibrium.
Because
Those
in a
kinds
real
of checks.
structure, there are number of loads.
Hmm.
Basically, usually the industrialistic there are 16
Hmm.
basic load cases:
Hmm. Hmm. Hmm.
wind, earthquake, and the
Yes.
equipment load, dead load, live load.
Dead load live
All
load.
those
Yes.
comprise in 16 load cases. So all the
Yes.
16 load cases should be individually, statically,
In equilibrium.
yeah, in equilibrium.
Yes. So these are the different checks that we need to know, and these and just by if you have enough experience of doing it, then you would know that just by seeing the deformed shape
Yes,
and the bending moment, you would know that if that looks right or something is wrong in it.
yes,
Right. So that kind of educated intuition as well as the yeah that intuition you develop only by knowing the basics and repeated practice. Right. So that is the whole purpose of taking this course, and that is why I believe even you have come to the course even
yes,
knowing that it can be done in a software, right?
yes.
So right.
The
Okay.
software
So
is like a black box, and
exactly, exactly. It
it's a
does what
real
you
problem
say.
nowadays.
Yes, it does what you say, but then we don't know what we have asked for is right or not. We might have made a mistake. We would know what whether we have made a mistake or not just by knowing the answer that it gives, right?
Yeah,
So that kind of intuition we need to develop. So that is why it's important to know the basics. Fine. Okay, so we'll get started. So I just want to ask a simple question that let's say we have a truss, what is a structure, truss structure that we can see here.
yeah.
So let's say that we have built a compatibility, the software is already available to us, or you have written a program where given the elements, it would give out the stiffness matrix for that structure, right? So
Mhm.
once you have that, can we find out whether this truss is first stable or not? Let's say you
Yes.
know the stiffness matrix of that this structure.
Mhm. But just knowing the global stiffness matrix, as already discussed, it's always its determinant is zero, which
Yes,
signifies that the support condition has not been considered in the
yes,
equation.
yes.
So means
But
the
but here
global
supports a
stiffness
given,
matrix
right?
by just by looking at you can't. I think I feel is you can't say that you know you have to look for the the whole equation.
Yes, right. So you're right that if we don't provide boundary conditions, then every stiffness matrix would become singular. Its determinant would be zero. So it would be unstable because without a boundary condition, a structure is
Yes.
can rigid bodily translate and rigid bodily rotate, right? So that is why it the stiffness matrix becomes singular, indicating that it is not stable, right? But let's say that we have given these boundary conditions to it, right? We are knowing some boundary conditions and we provide that boundary
Mhm.
conditions to the system as well, and after giving the boundary conditions, we would be able to reduce the stiffness matrix to a certain order, right?
Yes.
After that, can we, from the stiffness matrix, can we say that whether the structure is stable or not?
From the stiffness matrix. Right now, no idea.
No, that's fine. So that, yes, stiffness matrix becoming singular is an indication of instability,
Mhm.
right? So therefore, after supplying the boundary condition, still
The
if
reduced
the
stiffness matrix is a singular, then
is yes, then we know that the truss is unstable.
stable.
Okay, something, there is some problem with it is what we understand from it. So but before doing all this itself, we can apply Maxwell's rule and then see whether it is stable or not. But sometimes if there are too many elements, then what happens is that even after applying Maxwell's rule, it can show that it is stable, but it can so happen that it is unstable. We have
Yes,
seen
yes,
some
yes.
examples like that, right? But if Maxwell's rule itself says unstable, then definitely it's unstable. Okay.
Yes.
So now that, let's say that we don't want to go with Maxwell's rule, or some reason that in that particular structure Maxwell's rule is saying that it's stable, but still the stiffness matrix, reduced stiffness matrix is singular, then we know that it has become unstable. But how do we make it stable? That's a question. Let's say we have already, somebody has designed it. Now we know that it's unstable. We need to modify the system so that it becomes stable. What should we do?
We should add redundant bars.
True, but where? So let's say we have a big structure, and then the global stiffness matrix of it, let's say 1000 by 1000, as
Mhm.
we know that it's singular. Computer science says determinant is zero. So now where to add? Where will we add? We can add it anywhere, but adding anywhere will not solve the
Will
problem. We
not
should
solve the
exactly
problem.
know where there is a mechanism, where there are displacements without forces being applied,
Yes.
right? So how do we know that from what we have studied?
That's a good question, but I don't have the answer.
That's fine. So that is actually, I think, the need to study what we call as a compatibility matrix. Okay. So we'll
Mhm.
introduce a concept called as compatibility matrix, which is necessary to know what are the different displacements that can happen without any bar elongations. So without any straining in the material, mechanism kind of modes, if it can happen, how do we find that out? For that, we need to use a concept called as compatibility matrix. So it's very similar to how we built the stiffness matrix itself. Actually, when we built the stiffness matrix, that should have been built on basis of two matrices called as compatibility matrix and equilibrium matrix. Okay, and one more thing called as axial stiffness matrix. So these combination only gives rise to stiffness matrix, but we skipped all those steps and then we directly developed the stiffness matrix. That is why um I think it is important to stress the importance of each and every matrix. So that is why I brought this problem up. So let's say that we have a truss element which is oriented at an angle of theta, and what we are interested in is to develop a relation between displacements and elongations. So there will be an elongation in the stress, and there will be some displacements in the nodes. So how are these related is what we are going to develop. Okay, so it's very easy. So basically, let's say we want to know how much this stress is going to get elongated here. Okay, that will be just nothing but u1 sine theta, right? Because if this is theta, this will be 90
Yes.
minus theta. So we know that e elongation that is happening, let me just denote it as e1. E1 is equal to u1 sine theta plus u2 cos theta, right?
Yes.
Okay, but this is not the elongation, because elongation is this, whatever elongation happening this side minus whatever is happening this side, right? So e2, let me name it as elongation that is happening here. Okay, that will be, if this is u3 and u4, then I can say that e2 will be u3 sine theta plus u4 cos theta, right?
Yes.
So I can say elongation is nothing but, I can say elongation is going to be e1 minus e2. So I know u1 sine theta. So you can write what is e1 and e2 here. I'm skipping that step. But what I would like to show here is that elongation is a function of u1, u2, u3, and u4,
Okay.
right? So elongation in this bar, elongation, let's say it's in this one bar. Okay, elongation in one bar, first bar is equal to, is a function of the nodes that are connecting here.
Mhm.
Similarly we can do for all the bars that are inclined here, right?
Yes.
So all the elongations in all these bars can be related to the nodal displacements. U1,
Yes.
U2, U3, whatever is happening. Let's name 1, 2, 3, 4 nodes and we can relate it to the displacements. So once we do that, we would be able to write elongation as something, okay, some matrix C into this U matrix. U matrix will contain where elongation would contain all the elongation terms. Okay, elongation is a vector of E1, E2 and so on till En. Okay, where n will be the number of truss elements. Okay, and then what will be C? C will be a matrix. What will be U? U will be,
U1, U2, U3,
yes. So it will have U1, U2, U3 till what? Till
U1.
some U. Let me name this as M. Okay, instead
Mm-hmm.
of n, let me name it as M, where M denotes the number of elements,
Members.
and let me name this as N, where N denotes number of
Uh, Degree of freedom.
degrees of freedom. Exactly. So if there are n by 2 nodes, there will be n by 2 into 2 degrees of freedom. So total degrees of freedom is n. Okay, so and what should be C matrix? C matrix will be which
Transport.
connects these two. So therefore C matrix will be of size what? C matrix should be of size M cross n.
Yes.
Then U will be of n cross 1 and E will be of size M cross 1.
And
Okay,
cross.
so once we get this matrix, okay, so now what we can do is that what was the initial question asked? The initial question asked was how do we know whether a system is unstable is the first question. Second
Yes.
question is if we know that it's unstable, how do we know the displacements that are at what points are the displacements happening so that we can put some redundant members to make it stable, right?
Yes.
So how do we do that is basically we want to find all those displacements such that E is 0. E is 0 means what? Elongations are 0. When elongations are 0, it will be a mechanism, right? What does it mean when this total vector becomes 0? It will be 0, 0, 0, 0, 0. That will happen only if there are no elongations in the members, which will happen only if there is a mechanism, right? Everything is moving rigidly,
Yes.
right? So we have to find out all those u such that E is 0, right? So the question is, what are those u's which will give me 0, right? So this is called finding null space for a matrix. We can do this analysis. Okay, so in MATLAB, if you just say find out null, uh, I'm forgetting the exact command for it, maybe null. Okay, null of C, if you ask, then it will give all those u, let's say one thing is there, there can also be second u, and it will give all those vectors, u vectors, for which the elongations will be 0.
Okay.
Okay, it's a algebra problem, linear algebra problem. You need to find out those u's such that C into u will become 0. So
Okay.
since we know C, we have to find out u. This can be done very easily using linear algebra problem. So once you do that, all those u's u correspond to the displacements which can happen in the system without any elongations. So if it is a 1 degree of freedom, if the instability is 1 degree, that is there is only one possibility of instability, then there will be only one vector that we would get as an answer. Okay, if there are like 2 3 instabilities, then 2 3 vectors we will get as an answers. Okay, so once we find out these displacements, we know that okay, let's say if this has 0 0 2 4 0 0, then means that these degrees of freedom can displace without having any elongations in the members, all the members. That means that those degrees, let's say this is third and fourth, if you are saying 1 2 3 4, then third and fourth can move, is what we understand. So let's say these and this nodes are moving, then we can put a redundant member joining those two and see whether still the compatible the stiffness matrix is singular or not,
Okay. So is
right?
this the same method by which a software tells the location of instability?
Yes, if it is able to say, then definitely it is
In
using some
STAT,
sort
there
of
is
compatible.
a procedure to find the instability.
What is it?
Instead, if you model some maybe a trust member and you keep somewhere an unstable point, then after analysis, it will show a warning, and you can go to the post processing. There will be a command called instability. You can click there, and
Okay.
it will show the corresponding nodes. in which
Okay.
direction the instability is there for moment or for
Okay. Okay.
shear.
Yeah, if software is able to say the displacement that are happening as leading to instability, then definitely it's using some sort of compatibility matrix to predict it. This is a very basic or broad outline of what is compatibility matrix. So compatibility matrix is that matrix which relates nodal displacements to elongations that's happening in the bar. So this is external nodal displacement, and E elongations are internal. So it relates. This is a kinematic problem. There are no forces that we are talking about here. So it's just a kinematic displacement problem. So this is what it should be doing to find out what are the nodal displacements that are happening leading to mechanism, leading to those motions which do not involve any bar elongations. Okay, and usually we talk about this instability mostly in truss problems, because in frame problems, if you see, we do not encounter much of these things unless you have too many internal hinges and so on. Because let's say even if you take a frame something connected to this, then if the boundary conditions are sufficient, then it will automatically be stable, because every point, every junction gives three additional
Yes.
redundants, that is axial force, shear force, and bending moment, and every additional problem brings in three equilibrium equations, so they satisfy themselves, right? So if you just add a member, it will still be stable. Nothing can make it unstable unless you put some internal hinge into
Yes.
it and make it unstable. So that's why in frames we do not encounter much of instabilities, but in trusses it becomes very difficult to know whether a structure is stable or not.
Mm.
Okay, maybe these trusses are very obvious, but then if you have complicated systems, then it is actually difficult.
Yes.
Okay, so that is a gist of this compatibility matrix, right? And you can have similarly you can relate the forces to the internal bar tensions, right? So just like how we were able to relate the nodal displacements to elongations, similarly we can relate bar forces to external forces. For example, let's say you have this truss subjected to some force, right? F1 or something. Then you can find out there will be some bar tensions in it, right? T1 or something, and there
Mm.
will be bar tensions in it, which are nothing but bar compression or tension. I'm
Mm.
just assuming it as something. And then you can find out those T1 cos theta. So let's say this is theta 1 and this is theta 2, then you would be able to relate this T1 T2 with F1, because you know that component of T1, this is T1, right? At this point this will be T1, so T1 component will be T1 sin theta, right? So
Yes.
T1 sin theta plus similarly we'll have T2 sin theta 2, sin theta 1, this is sin theta 2, is equal to F1, something like that you might get.
Yes.
So similarly, you would be able to write at every joint how the tensions are related to these forces. This is the same as what you would be doing in a method of joints in stress problem, right? Same thing that we are doing here. Once you do this, what you notice is that you are able to relate the bar tensions to forces through a matrix which we call as the equilibrium matrix. This matrix you are already familiar with from the method of joints. So maybe you would not have written as a matrix, but you know at least these equations. You might have written this equation somewhere. So AT is equal to F is what you might at last end up with if you do this equilibrium for every joint, right? So where T is contains all T1, T2, all the bar tensions, okay, till Tm, where M is the number of elements,
Elements.
and F would contain all the all the joint forces, okay,
Joint
F1,
force.
F2, and so on, depending on the degrees of freedom. You might have two forces here itself, right?
Yes.
So every degree of freedom can have a force, so you can have till Fn. So here again we see that A will be a matrix of n cross m, T would be m cross 1, and forces will be n cross 1, right? So we can see that A is of size n cross m, while previously we saw that C was the size m cross n,
Mm.
right? So we see that they are reverse, and it so happens that if you arrange, you will know that A is actually C transpose.
Okay.
You don't need two set of equations. Actually, these equilibrium equations and compatibility equations are related by similar equations.
Mm-hmm.
They are not independently. Everywhere you get sin theta cos theta only, and it so happens that if you find one of them, the other is just transpose of it.
Okay.
Okay, it's a very interesting result. So what you can do is that you can use C equal to E and A T is equal to F. Okay, these two equations are this is actually these this is how this is one of the ways in which we can develop stiffness matrix. So this is what is compatibility equation, and this is what is equilibrium equation, right? And we can also have a constitutive relation which relates T to E, because we know that T is the bar tensions and E is the bar elongation. So if we have local coordinate, let's say G, which is the local stiffness of each bar, okay, so which will just contain EA by L. So EA by L for first element, 0 0 0 everywhere, then 0 EA by L of second element, and so on, and 0 0 EA by L of third element, and so on. Okay, so if you have something like this that can relate bar tensions to, I'm sorry, this should have been GE is equal to T. Yeah, because stiffness relates.
Yes.
Yeah, I'm sorry for that. So if you have this, then local stiffness of bars, right? So if you have this, then what we can do is that we can combine all this equation is constitutive relation, right?
Yes.
So we can combine all these three. How do we combine? We can write G equal to T, but E itself is Cu, right? So I can write G into, I'll just use a different pen or it's less confusing. So G, instead of E I can write Cu. Cu is equal to T, right? This is what we have. I have used these two equations now.
Yes.
Now what I can do is I can multiply A on both the sides because I know what AT is. Therefore
Yes.
I'll write AGC U is equal to AT. But AT is nothing but F.
F.
So I know what is this should be because we are relating U and F here. U are the nodal displacements and F is the nodal forces. Right? So AGC is nothing but I know that A is C transpose. So I can write C transpose GC itself. Okay, the same as this. This will be what? This should be nothing but the stiffness matrix,
Fitness
right?
matrix.
Stiffness matrix is what relates Ku equal to F. It relates the nodal forces to nodal displacements. Okay. So therefore K is nothing but C transpose GC. Okay. So this is one of the ways in which you can develop the stiffness matrix for the system. Instead of developing the way that we usually used to develop. How do we used to do is that we give unit displacements to those node and do it, right? You can do
Yes.
it that way, or you can just develop the compatibility matrix using this thing. And once you know the compatibility matrix, you can have the local stiffness of the bars, which is just EA by L. Every bar, what is the local stiffness, right? So you will have this, and then you can write C transpose GC. Then you will get the stiffness matrix for the whole system. Okay, this is another way of how to develop a stiffness matrix. If you develop this way, then you would also know the importance of what compatibility matrix is. That is why stiffness matrix contains all the three equations: compatibility, equilibrium, and constitutive relation for that entire system. Okay, because usually we tend to think that K equal to F is an equilibrium equation.
Yes.
that that is a global equilibrium, that looks like a global equilibrium equation for the entire system for forces and displacements, but the stiffness contains information of compatibility, constitutive, as well as equilibrium for the entire structure. Okay, so that is why we are able to solve the system just by this equation, and of course boundary conditions we need to know. Yeah, so that is how we are able to solve it. Okay, so this is one thing that I wanted to point out because we need to know the importance of compatibility matrix. Even though we can skip this step to get directly the stiffness matrix, but we need to know there is an importance for compatibility matrix itself. Okay, because to find out what are the displacements that can happen when there is instability and so on. Right? Okay. And then another point that I wanted to stress in today's session is there is a difference. What is the difference between a free body and an actual structure? right? So why, what I mean by that is, let's consider two cases, what we see to the left and to the right, right? So to the left we see that there is a simply supported structure with an applied end moment, right? And to the right what we see is that we are seeing the uh, forces, the what will be the free
Reaction.
body of this is the free body of this diagram. So when we have a moment here, we know that there should be an upward moment here and a downward moment which will cancel this whole things this moment. So that's why we have an upward and downward moment. So this is a free body, but somebody gives us this free body and somebody gives us this actual structure. Are they both equivalent? Will they both have similar displacements, similar kinematics? Is a question that I wanted to ask.
Okay.
Or another way of putting that question is, if somebody gives this, can I draw the structure and find out and analyze it? If somebody gives me only the free body, is it possible to find out the displacements in the structure?
No, sir.
Okay, so why not?
To know the forces, resolving the forces.
Resolving the forces, I didn't understand it. So my question is, just by knowing the free body, do we know the structure? If not, then why don't we know the structure? Why is there any other structure that is possible from this free body?
Yes, because you have shown a moment there. It can be a
Yes,
fixed end.
yes. So,
The constraint can be different,
okay.
which
So,
can
can you give
produce
me a
the same
structure
result.
which has the same free body?
Um, Downward reaction. It can be a prop cantilever.
A propped cantilever with the what force?
Prop cantilever uh, with an upward force along the. Uh,
Then it is on the support, right?
yeah,
So,
it is on the support.
you can just have a cantilever, right? What is the free body for this
Exactly.
cantilever? Right? The free body for this cantilever will also be the same thing, na?
Yes, 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 yes.
So that is the entire thing that I wanted to stress here. A free body is actually different from an actual structure, because a free body can correspond to different structures. It doesn't say about the boundary conditions. And
Mhm.
another, but what do we get from a free body is the internal forces. The internal forces for this, what this means is that both these have same free body, means that I the internal forces for both these structures are same, right?
Mhm.
Because internal forces are entirely generated from free body,
Yes.
right? So internal forces are same, which means that internal elongations or internal deformations are same, which means strains, curvatures, and other things which are deformation, relative displacement, right? Those things are same, but the displacement themselves are not same,
I'm not saying because
are not same.
there
Okay,
we can
that
have a
we do.
slope, but there we cannot.
Yes, exactly. So if we draw the deformed shape of these two figures, what do you see there? The first one would deflect something like this. The second one would deflect something like this, right? So how do we know? Then what is the relation between them? If we say that the deformations are same, then why they are not looking same? Or how do we show that these deformations are same in both these structures? Or in other words of asking, how do we use information of one thing to say something about the other structure? Can we use can we relate these structures in certain way, or they are entirely different? We need to analyze this as a cantilever. We find out that delta is equal to pl cube by 3a something, right? And okay, the way in which I wanted to ask is, another way to ask the question is, I know that the deflection here is pl cube by 3a, okay? Let's say I have memorized it, but now I don't know what is the deformation that's happening here. Okay, I don't know theta. I also know what the theta is here. Okay, what is it? I think it is
PL square
PL squared by EA,
two
yeah?
EI
2A,
two
2A.
EI.
Okay. So let's say I know this information, but how do I use this to predict this theta? Can we use, the question is, can we use some information from this to this? Are they both related in any sense? Because we know that the free body of both of them are the same. Should it be yes or no? Okay, let's take some examples to understand this better. Let's say we have a guided fixed roller, or guided fixed structure, right? Like one side is fixed, another side is guided, and we are applying a force on the guided end. Now there will be a deflection, right? Delta. Can we find out it? Maybe it's possible from structure analysis, yes, but
Yes.
I wanted to find it quickly, very easily, instead of doing a complicated. It's an indeterminate problem, right? So I would have to do uh, detailed structure analysis to find out the deflection. But if I want to find it out in a minute or so, then what should I do? All I know is how a cantilever behaves. Okay, I know PL cube by 3a, I know PL squared by 2a, but I don't know anything else. So what should I do? So how do you think the deflected shape of the structure would be? We can find out that, right? So it would be
Yes.
something like this, right? It would be having zero slope at both the ends,
Right.
right? And what else do we know about the structure? We know that if you draw the free body of the structure, we will see that it will have, there is a force here and there will be a moment, right?
Yes.
And since there is a force here, there will be an opposite force here, and the moment will be this way for this. Moment will be um, this way for this, right?
Yes.
How do we know the direction of moments? What I did was I just
From
used it
the
opposite to the way in which it deflects.
upper
Okay, so yeah,
balancing
so
limit.
from these figures you would be able to find out that this is actually two cantilevers, because even if you draw the bending moment shape for this, you would know that one side the moment is anti-clockwise and both the sides it's anti-clockwise, right? So
Mhm.
what you would see is that you will see a moment like this, moment bending moment shape like this,
Yes.
right? So once you know this, the bending moment shape, you know that this triangular shape is corresponding to what is it? It is similar to a simply supported with a moment or a cantilever,
It's a
right?
cantilever.
With a end force. So I can just treat half of this thing. I can say there is a internal hinge there. If I give it or not, it doesn't matter. Anyways, the moment is bending moment is zero there. Okay.
Mhm.
So what I can say is just half of this structure behaves as a cantilever. Okay. I think we have already done this during our
Yes.
stiffness matrix derivation. So if this is going to be P, I know the force that is going to come here is also going to be P. Okay. There is a P here downward and there is a P here upward. Okay, that means this part of the cantilever will be same as this thing. Okay, if this is same as this, which is same as this. Okay, so that is how I know that the deflected shape, I know if this is going to be P, right? So I can know that the deflection here should be
Then
P L Q L by 2 the whole cube. Okay, because the length of this cantilever is only L by 2 by 3 right? That will be the deflection, and into 2 I have to do for to find out deflected deflection of the whole thing. That is all. So I can easily find out what is the deflection that is happening in a guided fixed roller. So guided fixed is nothing but two cantilevers. So once I understand this, most of my problems which seem to be complicated, we can actually compare it with the known things and try to understand them better and get out of the fear of seeing complicated boundary conditions, right? So that is why I wanted to emphasize. So here another thing we have given is a simply support. A simply supported can be related to a cantilever in what sense? Right, with a midpoint loading, how can it be related to a cantilever? If we draw the bending moment, then we can see that the bending moment will be something like this, right?
you can see the
So we can see that it is made of two triangles, right? So this triangle, I know it's similar to a cantilever. So the deformation that's happening here, I can just imagine that there is a cantilever here with an upward force. So I can say that this is a cantilever with an upward force. That
yes.
is all I can analyze. So basically it is in fact entirely true. What I mean by that is the deflection shape that is happening in a simply support, and if we have a cantilever with the same loading, whatever deformation happens here, I can just take this, pick it up and put it here. It will overlap exactly like a tracing paper, right? It will exactly overlap. All the deformations that's happening here will be same here because the bending moments are the same, right? So if bending moments are same, then curvatures will be same. If curvatures are same, then strains will be same.
Yes.
Okay. So it will entirely overlap. So it's nothing but two cantilevers, that's it. So we can find out the deflection in a simply support with a midpoint loading, which we might have already memorized. But even if you forget, we can find out using the concept of half cantilever and try to find out this will be p by 2, right? Because simply support, if p is applied, then the support will be p by 2. So I can say that this is p by 2. For p by 2 and L by 2 length, what will be the deflector if I find out using PL cube by 3a formula? Then I can directly find out what delta is. This delta will be same as this delta, right?
PL
So we
cube
can,
by 48 EI.
yes. So we would know that even if we forget it, we can do this. It's not about just trying to derive it. It's just about understanding that they are the same. Okay, that
Yes.
understanding can go a long way in helping us solve many other problems. Okay. So wherever you see some structures, you should be able to relate it with a cantilever, a simply support, or anything. Basically, whatever I have seen, I am able to relate it most of the things to cantilever itself, because even a simply support is related to a cantilever. Therefore, so anywhere you can directly say which end is fixed and which end is free, and what can you do with it. Okay. So that's a way to develop an intuition towards these structures. So coming back to this question, what I asked was, how do we relate these two structures that their strains and curvatures, deformations are all same. So if I take the structure and put it here, it will exactly overlap. Only thing that I have to do is that I have to make the slope, this thing, to be tilted here. So it's like a cantilever here with this bending. Okay, so
Mm.
this deformation will be PL cube by 3a. This will be the axis of the beam initially. Okay, so if you are good with maths, then you can actually find out what is theta here just by knowing this thing. Okay, relating PLQ by 3 and other information, you will be able to actually derive what is theta. Okay, so that's what you should know, that it is just an rigid body rotation of this thing to get the deformed shape of a simply support with an end moment. Okay, fine. So that is one thing that I wanted to stress this point. And okay, so one more problem, let's consider. Let's say we know that there is a frame, okay, L frame, and there is a N force that is applied to it. So can we find out the deflection that is happening at this free end? How do we find it out?
Here also we can use the concept of cantilever.
Yes, how do we use that?
First of all, we need to know the position of the node before it.
Okay,
Yeah.
let's say this is L and this is also L. Okay,
Yeah.
so how do we know it? How do we find out? So
First of all,
basically, yeah,
the load will be transferred in this point to the
to
left.
this point.
Okay,
Yes.
so it will create a moment also.
Okay,
So
good.
that moment there will be certain deflection
Yes.
at that point, and that
So this
deflection
is
will.
going this is going to be PL, and there will be an axial load P.
Yeah.
Okay. And this PL, we know what will be the deflection and rotation it causes, right? So
Yes.
we should know everything about a cantilever, then we can analyze most of the
Yes.
structures. So if you know, if given n moment, then you can find out what will be the rotation and deflection that's happening
ML
there. Okay.
square by 2 EI.
2EA and PL by EA, right?
ML by EI.
Yeah, so you can find those out. Then you say that this structure itself is again another cantilever,
Mhm.
which is subjected to a P n force and an n moment of PL, right? And then there'll be again opposite of this, right? P. So that will be starting from this point, whichever angle this has rotated. From that point, it will rotate further.
Yeah.
Okay, I have
That
exaggerated a lot, but the idea is that this is what. So this angle itself you should know first, which you can find out from
ML by
cantilever.
EI.
Yes, and after that, the deflection anyway would not matter. You would have the entire system to be rotated. So therefore, if you have a cantilever with an end load, you know what is the deflection. But now this cantilever itself is positioned like this. Okay,
Mhm.
so
Yeah.
there will be a rigid body rotation. Theta into L will be the total deflection that's happening
Yes.
here,
Delta.
and on top of that there will be a deflection. Okay, that deflection you know. So theta L plus PLQ by 3a, where theta is the theta that's happening in this vertical member.
Yeah.
Okay, So you would be able to do that to find out what is the deflection that's happening in the frame, right? So that would give a physical intuition of how actually it deforms, right? Okay, so I also have a few problems now. Just I thought it would be fun, right, to predict the deflected shapes. So just to check the kind of understanding intuition we have. So can you predict the deflected shape? We'll start with very simple figures and then we'll go to a bit more complex figures in the next slides, right? So can you predict the deflected shape for these structures? You can say how it deflects starting from bottom to top and center. There will be no deflection or something like that. You can say so that I can draw it here.
Okay. For the second structure, I can say
Okay, second structure, what it is?
first it will be a hogging
A
for the left,
hogging here. Okay.
and then it will be sagging.
Okay, good. So at midpoint?
At midpoint, it will just pass with some slope because there
Okay,
is a
okay,
moment applied, so it will
okay. Good.
have
So yeah, so I think you're indicating something like this, right?
yes.
But the question is, the slope here will be higher or the slope here will be higher? So
If
what I
it's
mean by that is,
if
if
it's equal and the geometric property are same, then it will be equal.
equal, should it be equal? Think about it. What I'm asking
Mhm.
is, would it look something like this, where slopes are equal, this half, or would it look something like this?
Okay.
Okay, where the slope is higher and the slope is lesser. I hope we are able to see the difference between these two figures,
Mm-hmm. Yes.
right? So here the slope is higher and here the slope is lower.
Slope is
Okay,
lower.
so which one would be right?
The second one should be right.
Why is it so? And there is a third one where you can have slope to be higher here and the slower to be here. Okay,
Mm.
which one should be right?
Okay, if you think it,
Everything
we need to
seems
think.
similar.
We need to think like a cantilever, right?
It's similar to a cantilever, or can you split it into two things here? You can split it
We
into
can
two
split it
simply
in two
supported.
things from whatever we have learned, and
Yes.
also
So one thing we know that is the deflection at this point is zero, right?
yes,
So can I just introduce another hinge here? Will it disturb anything?
no,
It would not. A hinge will basically want the displacement at that point to be zero. Rotation it allows.
yes,
Only displacement it wants to be zero, but anyways we think that the displacement is going to be zero. So it would not. Nothing will happen if I just introduce a hinge, an external hinge there, right? So if I do that, I can split this into two problems. One is this problem. Another is this problem, where this will be m by 2 and this will be m by 2.
right.
This is similar to what we have studied in the basics of displacement methods. The
Mm-hmm.
total moment is trying to rotate both these things. The stiffness from both these members will contribute towards the entire structure. Okay, so they are in
1 plus 2.
series or parallel.
They are in
So
parallel.
yeah, they are in parallel.
Their
Mm,
scopes will get added.
yes, okay. So
Yes.
this moments are getting split into two things.
Mm-hmm.
So we know that for a simply supported with a moment applied, what will be the deflected shape?
Mm, yes.
It will deflect upward, right? And if when it deflect upwards, the rotation here should be higher, and the rotation here will be only half of it,
Half of it because moment
right?
was half.
So this is right. Third figure is right. Is it
Mm-hmm.
not? So when we draw a deflected shape, we should be careful and conscious of how we draw it. Not just that, okay, this is some rotation hogging, sagging. That is true, but we should also know that we should be conscious towards how the actual deflected shape is. Okay.
Mm-hmm.
Sometimes we miss it if we are not concentrating on it, but we should at least try to be as much accurate as possible.
Yes.
Okay, so this rotation will be higher than this rotation. So this will be the deflected shape for the second figure, right? And it so happens that this theta, if this is theta, this will be theta by 2 and this will be theta by
Mm-hmm.
2. Okay, okay. So this problem is done. What about the first one? Hmm? We know that the rotation here should be downward. We know that the rotation here should be upward. From
Okay.
symmetry, we would be able to guess that okay, here also it will be something like this only, right?
Yes.
Okay, good. But again, the question comes: where should the rotation be higher? Where should the rotation be lower? Should it be like 1, 2, or the third one? This again, we
Rotation
know that the
should be at higher at the applied load points.
yes, because if we split it into two problems again, which we can do because the central point we don't expect it to displace. So we know that this is something like this, therefore it will have a displacement like this. And second thing is like this. So we can see that here if it is theta and theta, this will be 2 theta. Okay. So that will be the rotation. So therefore this deformation would not be similar to this deformation.
Yes.
Okay, they cannot be overlapped because here it is higher and lower, here it is lower and higher, right?
Yes.
Okay, good. Any questions from this problems, or can we move on?
You can.
Okay. So here the next figure, which is quite simple only. We just have a simply support overhang. What would be the displaced deformation shape of this?
Uh, Deformation shape is the left part, the cantilever part will be, there will be hogging moment, and
Okay.
sorry, hogging moment.
Okay.
This part will also have hogging moment.
Okay. So
And
as you said, this part is like a cantilever where you have a load, so it will hog, right? And the
yes,
bending moment here, whatever was given here, the same moment it will give to that structure. Therefore, there is a simply supported here with that moment. Okay.
mm,
But when I say it's a fixed end, we don't need to have the rotation to be zero there. What I
yes,
mean that is there will be a moment there.
yes,
Okay, so we can have a non-zero slope there, but only thing is that we know there is a moment, so because of that moment it will hog here, so we can say that it will be something like this, right?
yeah.
And
Higher
okay, we have to
rotation
be
at
careful when we draw it because this angle will be lesser,
yes,
this angle will be higher, because same thing, the moment is being applied here,
mm,
and whatever is a rotation starting from that point there will be a cantilever. Okay, something like this. I have exaggerated it a bit, but the concept is that you have to get the angle here, and from that angle you should have a cantilever-like deformation.
yes.
Okay, fine. I think this is understandable. Good. Okay, so this was pretty easy. Let me introduce one more force here and then see whether you're able to solve for it. Let's say there is a P again here, which is at a distance of L by 2 from this point, which is at mid-span. Okay. Then what will be the deformation shape? This is
Uh,
actually a very interesting problem.
yes.
If you can, you can even solve it numerically and find out what are the support reactions and deformation shape.
Yes. Okay. So
Maybe we can do it together so that it takes less time. So what we can actually do is that when you, this is a determinate problem, so you can use, you can find out the support reactions directly, and you would actually see that this will be the free body. For this, I'm directly drawing it. You can verify it when you are free.
mm,
So this will be 2p, this will be p, and this will be p. Okay, which means that this should be
this is zero.
exactly. So this will be 0. What it means is that the support does not contribute at all. Okay, now
Yes.
let's say this is the free body. How do you verify it? Because p into L by 2 plus p into 3L by 2 will be 2p into L. Okay,
Yes.
therefore it satisfies moment equilibrium. Therefore
Equilibrium.
whatever support reaction that we have drawn is right. Okay,
Right.
now can you find out the deformation shape for the structure from the free body that you have seen here?
Yes.
This
So,
portion is similar to what?
from P to P, it will be hogging, and then
Okay,
it will be sagging.
p to 2p it will be hogging, 2p to p you are saying it's sagging.
No, no, no. From P to P, it seems hogging,
P to P it's hogging, okay.
and after that, it should be sagging.
After that it's sagging. But
Yeah.
after that there is no moment, right?
Yeah. After that, there is no moment and no force, so it
Yeah,
will just
so why
go
should it sag?
linearly.
It should be straight line, no?
Yeah, it will just go linearly.
So if you see the blue portion, can you feel that it is an inverted simply supported beam?
Yeah.
So it should behave like that, right?
Yes.
So it should be an entirely same bending moment. I mean, same curvature. It should be either positive or negative.
Mhm.
And we know that it will hog, right? Because if you have two P and P, it will hog.
It
Okay,
was acting like a bow.
acting like a
Bow.
what? I didn't hear.
Bow and arrow. Bow.
Ah, yeah, bow. Yeah, exactly. So you have a bow. In fact, yeah, same as simply supported. Even simply supported acts like that, right? So yeah, so bow. It becomes a bow, right? So you can have, you know that the deform displacement at this point should be zero.
Yes.
Okay, and we know that it is going to hog. The only way it can hog is like this. Okay,
Yeah.
then I'm just redrawing it. So we have zero, not zero. That's a hinge. Okay, it's a triangle, and then we know that the hogging should be something like this because it should be zero at this point. Displacement should be zero at that point, and then it should hog till here. That much we know. Okay, so this total portion should look like a upward simply supported beam.
Yeah.
It should have similar curvature like a simply supported beam. So it will be something like this. Okay, just like if you have a simply support with an AF force like this curvature, this bow should be same as this bow.
Yes.
Only thing is that it is just put in a tilted format at this point. Okay, that's the only difference. I have drawn it more curvature here, but then my idea is to say that the curvature will be same. So it should have similar curvature, something like this. Okay, this is what is happening here. So only thing is that from the boundary condition we know that the displacement should be zero. So then what about this point? How do we do this? What should it be? We know that it's a straight line,
Yeah.
right? So how do we connect it?
We can draw a tangent there.
Yeah, so actually the tangent at this point should be towards this point, okay? So it should be something, it should not be curvy, it should be straight line, and that tangent should be there before drawing it, okay? So you should be very careful when you draw this problem. It's a straight line because when you start from here, you see that there's no bending moment.
Mm.
So we know to know that it's a straight line. From straight line, that tangent, you have to keep it up
We'll start a
and you
perpendicular.
have to draw the bow. That's how that bow should be. Okay. Then the question comes on, what is the purpose of this support? What is the support doing?
Stability.
It's not doing anything. It's giving zero support, right? Zero reaction.
Yeah.
So can I just remove this off?
If you remove it, then it will be acting as the unstable structure.
But now also it's not supporting. It's like you have a support and the beam is not touching there. It's like just, it's not doing anything. Can I remove the support off?
Theoretically, you can remove, but
Hmm.
practically, it doesn't seem like a stable structure.
Okay, if we remove, then what is it standing entirely on? It's like
It
just
just
like a
on a
what?
roller,
Yeah,
just
in
like
a
a
roller.
seesaw.
Yes, right. So basically, we would have it like a in a physical balance. If you know, in a physical balance, we would have a
When a
support and then there will
seesaw
be
is balanced.
exactly. So it is like a seesaw where you have equal and opposite forces, and entirely it's balanced by the middle point.
Middle
The
point.
only thing it is doing is that the entire seesaw can be like this or can be like this, still it will be in equilibrium.
Mm.
Anyway, it is there in first order theory, it will be in equilibrium. Okay, so
Mm.
the kind of structure analysis that we are doing in that it will be in equilibrium. So when we do that, we observe that what the support does is it decides what this should be. Otherwise, the deflected shape could have been something like this also.
Yeah.
Okay, so the deflected shape, the displacement is dictated by the support condition, but the deformations are not contributed. The support does not contribute anything towards the deformation.
Mm.
Okay, or the stresses or strains, or it just says that the seesaw could have been something like this. It's just making it rotate and then come here. It's like a freely it will rotate like a rigid body and come here.
Okay.
Okay, that's what the support is doing, nothing else. It's just ensuring that the displacement at this point is zero. Fine. Okay, so this is an interesting problem that I encountered. That's why I thought I would share with you.
Yeah.
We have many other structures. Then probably we can discuss in the next session, which would be our last session, I guess.
Mhm.
Uh, yeah, because I think we are running out of time.
Yes.
So probably I'll just send this questions to you because it will be there in the resources folder,
Yes.
and then you can try it out and see you are able to find out the diffracted shape for that. And if you are
Okay.
stuck somewhere, then we'll discuss it in the next lecture. Right?
Sure. Sure.
Okay. Are there any more questions that you would want to ask?
No, not for today.
Okay, fine. Then we'll stop the session, today's session here.
Mhm.
Okay, then. Thank you for attending.
Thank you.
Yeah,
Bye.
we'll meet next week.